In this clip, I'm going to put together the big picture of, well, no surprise, disorder, entropy, and the second law, and how that all relates to heat pumps and heat engines. So let's begin by speaking about entropy itself. When I say the word entropy, it may seem confusing to you, but if you always just translate that in your mind to the word disorder, you are in good shape. So, disorder, as it turns out, is a very important item in the universe itself. In fact, I can kind of show you here. Let's look at a nice way to understand disorder and its ramifications. Okay, so what I'm doing here is I'm drawing a tank. It looks like two tanks, doesn't it? With a little lump in it. But this tank, on one side, the red side, you have heat, right? It's hotter. So imagine that's got water in it, and that water is hot. Now, this whole tank is insulated. And on this side, we have cold. So it's like cold water right over here. This side is insulated too. So you might be wondering, okay, well, yeah, but what's this part? We can imagine that this is kind of like a very thin, maybe a cellophane division in between the two parts of the tank. So you've got the hot part of the tank over here, cold part over here. So the molecules themselves can't pass from one to the other, but heat can flow from one to the other. In fact, let's draw this. Okay, we know that heat's going to flow from hot to cold, and I always like to symbolize heat with this Q right here. And whatever heat, so we'll say Q out of the hot has got to be equal to Q in of the cold. Each one is in joules, so you'll have a certain amount of heat in the form of joules flowing out, or whatever units you choose, flowing out of this hot region and flowing into this cold region. So what goes out must come in, all coincides with the energy equation. So this is no surprise. But now let's start looking at the surprise. Okay, to set this up, what I want you to do first is I want you to look at, you've probably been wondering why on earth I have these pictures of parties. This is a 5-year-old birthday party. So 5-year-old. And this is a rather sedate picture of elderly people at a party way back in the day. And we're going to call this, for purposes of assumption, the 80-year-old birthday party. So as you can imagine, there are quite different dynamics going on at each one of these parties. At this party, the youngsters are lively, they're crazy, they're running around. In fact, they're acting like high temperature molecules. High temperature molecules. So if you might analogize, let's see, you've got this water molecule, and what's it doing? Here's the oxygen and the hydrogen, and so if it's at high temperature, it's rotating around, and it's also vibrating, so it's like narrow sometimes, and then it expands, so and then it's moving in and out with the other molecules and kind of bumping into them. The hotter it gets, the more motion you've got, the more frenetic the energy. And that's the way it is with this 5-year-old birthday party. So you might think of this as just high temperature. Okay, what's going on over here? Well, you've got some very sedate individuals. So we can call these low temperature molecules. and they like to sit around and not move too much, so there just isn't much action going on. Now, can you imagine that if I took one of these low temperature molecules and I put it over here at the 5-year-old birthday party? Well, you know, it really wouldn't make much of an impact because these guys just don't move around very much. They're not very lively. But the 5-year-old, if I took that 5-year-old and put it over here in the 80-year-old birthday party, oh my goodness, talk about the upset. Even one 5-year-old, unless you kind of put the kibosh on them, would not, they would do a lot of, add a lot of liveliness to this birthday party. So what am I really saying here? Now remember, entropy is disorder. You can imagine that when you have a high temperature situation where you've got all sorts of moving molecules that are lively, there's a lot of disorder. There's a lot of entropy there. But low temperature molecules, these sedate individuals, they don't have much by way of entropy. They're very sedate, so there's not much disorder going on in these kinds of parties. So if we look back at our vat of water that's separated by this cellophane, the high temperature region is the equivalent of high entropy, or it has high entropy. The low temperature region has low entropy. Now what happens when we allow some of this energy from the high temperature to flow into the low temperature? Well, guess what? We remove entropy, so the entropy here decreases. And the entropy here, obviously, increases. But the trick is, this is different than the heat that's flowing out of here and into here. Here, what flowed out is equal to what flowed in as far as joules goes. But for entropy, the amount of entropy that flowed out of here is smaller than the amount of entropy that flowed in here. Why? It's just like this. If we take an old person and put that person in the birthday party of the youngsters, well, they won't make much difference, right? So it's not like a perfectly equivalent back and forth. If we put something over here, it's the same as putting something over here. The actions are very different. Look, we put the 5-year-old over here. Wow, that causes a lot more disorder. So that's why entropy increases more when you have heat flowing from hot to cold, right? So in other words, the entropy flowing out of this hot region is actually less than what flows into the other region. So this leads us to the second law of thermodynamics, sometimes paraphrased as no such thing as a free lunch, but more formally we can say the entropy of a thermally isolated system. See, there you go. It's thermally isolated. It's got all these insulation around it, of objects never decreases. Okay, now that's sort of the legalistic way of saying it actually always increases, unless you really want to get right down to the nitty-gritty. But in general, it always, always, always increases, or at least stays the same. So you might want to say that, okay, well, that's the case here for this, but what about the universe as a whole? The universe as a whole, we can think of this whole area right here as sort of being the equivalent of the entire universe. And if we did that, what we would find is locally we can reduce entropy in some places by allowing heat to escape, right, and other forms of structuring our whatever we're looking at. But overall, We must increase entropy through any physical process that occurs. Now, this has deep, deep ramifications when it comes to something like heat pumps and heat engines. So let's go back and let's look at the big picture of heat pumps and heat engines and how they relate to one another and what this second law of business means in that regard. Okay, so we're going to draw our hot reservoir. Helps if I spell reservoir. And remember, the hot reservoir is going to be at some high temperature, which we'll call TH. So you might think of it as like 500 K or something like that. We'll put some actual values in there later. And what we'll do is okay, so we got our cold reservoir right here. Okay, here we go. So cold reservoir. Okay, and that's at some cold temperature right here. So what have we got going on? Let's compare a heat pump and a refrigeration unit. And a engine. So we're going to look at heat pumps and engines. Okay, here we go. This is our heat pump. What are heat pumps doing? They're causing energy to flow contrary to nature, from cold to hot. And how do we get it to do that? Simple. We add some work to it. Okay, so we're taking sort of cold heat out of our, like this might be the freezer compartment in my little refrigerator. We pump it up, add some work to it, and voila, there's our hot heat that we're throwing out. So this is a heat pump. I'm going to tell you 3 common ways that we can have heat pumps. And one is what? Air conditioners. And if this is an air conditioner, what does that mean? That means that we want this to be the inside of our house, and we want to throw heat outside the house where it's hot already, and that's the whole principle of an air conditioner. So what's number 2? Well, a refrigerator or a freezer, same idea, refrigerator. Now what happens if we've got a refrigerator? Well, simple. This is our cooling compartment right here, and we want to take our heat and throw it outside into the room. So in this case, it would be like this is the kitchen. Now, I might ask you all these kinds of questions, like what's where for a particular device. Where's the cooler? Is minus QC coming out of the cooler in the refrigerator? Well, the answer obviously is yes. But let's say I tried to trick you and say, is QH flowing out of the refrigerator for a refrigeration system? Well, it's flowing out of the outside of the refrigerator, but it's not flowing out of the freezer compartment itself. Remember, this part is this minus QC is what's flowing into the evaporator, and this part right here is what's flowing out of the condenser. So now, let's see, we've got that figured out here, and I want to draw the equations that are affiliated with this one right here. So we'll put these equations. QH is equal to minus QC plus W. That's no surprise here. Look, this one value right here is equal to these 2 values that are flowing out. Okay, yeah, that makes sense. And then the second equation is minus QC is equal to W times TC over TH minus TC. Now, one thing I want you to notice, the amount of work we put in is related to how much heat we can draw out of this cold region by this ratio right here, which is a really important ratio. Now you can see, look, when TH and TC are very far apart, this number is going to be really small. That ratio is going to be very small when these numbers are far apart. So what that means is you'll be able to draw less heat out of this cold region for a given amount of work if the temperature difference is very big. So in other words, what I'm really saying is this is not very efficient. Heat pumps are not very efficient when the temperature differences are big. So that's why you don't see heat pumps in areas like Alaska or far north regions where there can be very big differences in temperature. And so that actually brings me to number 3, which is heat pumps. That's the third common use. And what a heat pump is, it's a little different. It's precisely the same idea as air conditioners and refrigerators, but we flip around the important parts. So for an air conditioner, you had the house was your cold reservoir, and you're throwing out the heat outside. But for a heat pump, you just flip around the outlets of your heat pump. So now you want your hot reservoir to be the house itself. You want to warm up the house. That's what heat pumps are used for. So you take cool air from the outside, compress it with your compressor, and then use it to warm your house. This works great in places where, like Mississippi and so forth, where it's not very bad in the winter. It doesn't get really cold. But for places like Alaska, this simply would not work very well. It's not very efficient. Okay, so now what I want to do is contrast this whole idea with that of a heat engine. Now, heat engines work the opposite way. What they're doing is they're taking heat out of a hot place. So because I'm taking it out, this minus sign only means I'm removing it. So it's minus QH, and here we go. This is falling out now. What we're really doing is we're stealing part of that heat as work, and the rest of it we're throwing out as QC. So here's how you think of it. This hot region is like the spark plug in the engine when it fired during that power stroke. That's the hot, okay? We're taking some of that heat, we're removing some of it as work, and we throw some of it away out the muffler. So what comes out of the muffler is actually still warm. Now you might say, well, wait a minute. Why don't we just work it so that we take it all out as work, right? So why can't we just take all the heat and make it all into work? Well, because again, there's no such thing as a free lunch. We can only take out enough heat and siphon part of that out as work to fulfill the limits set by the second law. In other words, we can't take all disorder and put it into order. We still have to create enough disorder through this whole process to increase the general disorder of this whole area because of this process. Again, there's no such thing as a free lunch. Every process you have must essentially increase the entire disorder of that process caused by that process. Even though locally you can create little bits of order, if you don't have this kind of disorder occurring, the process itself will not occur. So I know one instance where someone around this area in Detroit had actually devised an engine. He'd given up his job. He'd taken an early retirement, had investors investing millions into this process, this engine he had designed, and it was a very clever engine. But one of the things he hadn't done was to have a technical evaluation before he went to the patent office. So he came to Oakland University, asked one of our professors to look things over, and what was discovered was he was violating the second law. In some areas, he was positing that he could take all this work out, or heat out, convert it to work, and he could do so in a way that, well, was created less entropy or disorder than he had originally had. So that meant however good it looked on paper, it wasn't going to work in reality. Now so this is a heat engine right here. And I kind of talked about that stuff, but even above and beyond these ideas of entropy, the whole essence of an engine is you're taking heat and you're siphoning part of it off as work. So now I'm going to have, let's put all of this stuff right here for the refrigerator. We're going to put that in yellow. So I want you to remember that part is associated with the refrigerator, because I'm going to give you another set of equations right now, and that's QC is equal to minus QH minus W minus, okay, and look at this. QC, what we're doing is we're taking some heat out of here, subtracting part of it off as work, right? So that's minus W, and then the remainder is thrown out as sort of cold heat through the muffler. So this equation is equivalent to this top equation here, but this one is for heat engines. Don't forget that. So let's put all our heat engine stuff. I'm gonna add another equation there, so I'll make room for it. Okay. So heat engine equations I'm going to put in this purple, and let's do our second equation right now. So that's W is equal to minus QH TH minus TC, okay, all over TH, and we'll put this all in purple. Okay, and again, this is for heat engines, and up here is for heat pumps. Okay, we'll put that over here. Now, what I want you to notice about this expression, for this one, the TH minus TC, the temperature difference, is in the top, in the numerator. So what this really means is you're trying to get some work out, right, from the heat that you throw away. And the bigger the temperature difference, then what that means is the bigger this ratio will be. So in other words, the bigger the temperature difference between hot and cold, the more efficient your heat engine will be. So those are great questions I could ask. I could say, is a heat engine more efficient when the temperature difference is small? And then, of course, you'd say that's false. And I could ask, is the heat pump more efficient when the temperature difference is small? And of course, you'd say, yes, it is. So these just work in opposite ways. But this equation right here gives you the whole clue about which one is more efficient where. Okay, so let's work an example now. And what I'm going to do is I'm going to say that TH is going to be, we're going to set TH at a temperature of 298.15. Why? Because I just pulled that out of my head. And we're going to say that TC, our cold temperature, is going to be 233.15. So actually, this TH, that's equivalent to 25 degrees C, That's about room temperature. And this one's equivalent to about minus 40 degrees C, which coincidentally is the same as minus 40 degrees C. So it's really cold. So we've got these two temperatures. Now, can we use those if we have a heat pump? We've got a heat pump situation. Okay, and we're putting some work in. Let's say the amount of work I'm going to put in is 100 joules. Okay, so it's 100 joules. How much cold heat can I pull out of the freezer unit of my refrigerator given that amount of heat or work that we're putting in? Well, all we have to do is plug in. Here's our equations right here in yellow for heat pumps. And all we have to do is remember this temperature difference ratio that relates minus QC to W. So W is 100 joules in this case. And we're going to multiply it by this ratio, which is 233.15 over 298.15 minus 233.15. And this whole ratio right here is, that ratio is 3.6. So the amount of heat we can take out, well, 3.6 times 100 is 360 joules. Okay, and that's minus QC. So that doesn't look too bad. I mean, look, we put in 100 joules of energy up here in this heat pump, and what we get out is 360 that we're able to pull out of this and throw outside into the kitchen or wherever we didn't want it. But what would happen if I changed these temperatures? What happened if I made that high temperature be, instead of 298, what if I made it 500 Kelvin? We'll keep this one the same. So we've dramatically increased this hot region right here. So it would be like throwing it out into a kitchen that was really, really, really hot and people couldn't live in it. But that's okay. So we want to take some heat out of this freezer unit and throw it into this incredibly hot region. How much heat could we take out at that time? So let's try working it. Minus QC is equal to, let's see, well, we still got the 100 joules of work we're putting in. And this time we're going to have a different ratio. We're going to have 233.15 over, and the high temperature is 500 this time. So this is the high temperature that I'm plugging in, minus 233.15. Okay, we got it right there. So what does this ratio turn out to be this time? Let's see. If we compute it all, this time it turns out that the ratio is only 0.87. That's a lot smaller than what we had before. And in fact, minus QC in this circumstance with the much higher temperature difference turns out to be only 266.85 joules. So it's actually much smaller now than it was before, where the 360 joules. So what that means, again, is the bigger the temperature difference, the less efficient you're going to have as your heat pump. So the less efficient your heat pump is going to be. Okay, now let's try all of this again, but this time we're going to talk about a heat engine. So that means we'll have to be using these purple equations right here. So we've got a heat engine, and let's say that, again, arbitrarily, I'm selecting Q minus QH, that's the heat that we're pulling out of the hot reservoir, is going to be 100 joules. If it's 100 joules, and let's say we start again with this original 298.15 and 233 as our cold temperature. Let's see how much work we can pull out from this original heat? What percentage of it can we pull off as work? Well, simple. We're going to use this equation right here. We'll say minus QH is 100 joules. And we're going to have this ratio again. And this ratio will this time say 298.15 minus 233.15 all over 298.15. And if we work that all out, it turns out this time it's just going to be, well, let's see. We'll figure out what this ratio was. What did it turn out to be this time? It's 0.22. So that means we take out 100 joules, and out of that 100 joules of hot heat, we can only convert, well, 0.22 times 100 is equal to 22 joules, which is the work. Okay, so because we're plugging into this equation right up here, this one. So work itself, only 22 joules, small fraction of the original 100. What happens though if we increase the temperature again? What happens if we take that up to 500? Let's try rewriting it and see what we get then. We've got 500, that's what we've changed our hot temperature to, of the hot reservoir, minus 233.15, and then 298.15. Okay, what does that all turn out to be? That actually is a ratio that's 0.53. So we've got 100 joules times 0.53 this time. So that's 53 joules, which is the work we can get out. Again, this just shows that the bigger the temperature difference between the hot and the cold for heat engines, this is a heat engine, the more efficient that heat engine will be. And that's the opposite of that for heat pumps. Here, the bigger the temperature difference, the less efficient that heat pump is going to be. Now let's work a couple of example problems so we can see exactly how we're supposed to be doing the kind of problems that they assign in your textbook. So first we'll work problem 8-8. The whole trick, remember, to solving these kinds of problems is to figure out what the different quantities are. For example, QC, QH, and work. So this is a heat pump. They outright tell you exactly what you've got, a heat pump. Same as kind of the same idea as an air conditioner and as a freezer and that kind of thing. So we know what we're going to do is we're going to cause energy to flow against the grain from cold going over to hot. So here we go. We've got this heat pump here. We know we're going to take cold energy out of the cold reservoir. And for example, this would be, well, in this case, they're saying it's a heat pump. So what we're trying to do is this is going to be the inside of the house that we want to keep cool, inside of house. And this is going to be the hot outdoors. So we're going to proceed to make it even hotter by throwing some QH into it. Oh, I should have had a minus here for it's coming out, so we'll call it minus QC. We're taking out that cold heat from our house so we can make it even colder. We're applying a little bit of work, actually maybe a fair bit of work, and we're going to use that to pump it up to a higher temperature and pressure and throw it out the window, so to speak, so it just goes outside and makes our house nice and cool. So we've got to have the heat pump equations, and we'll write those down. We've got minus QC is equal to W times TC over TH minus TC. And, oops, so I'll write it like that, equal to. And then the other equation that relates to heat pumps is QH is equal to minus QC plus W. So remember, see, minus QC plus W must add up to this QH right here. These are our two fundamental equations. Remember, this one is the limiting equation that says that's the best we can do as far as the relationship between how much heat we can pull out of our house, for example, given a certain amount of work, is dictated by what those temperatures are. And the best we can do is given by this ratio, which is dictated by the temperatures. So let's give some temperatures to do the dictating. Here they go. Right here we've got 300 degrees, and let's see, that's the hot house, so it's 300 K in the hot house. Outside, 260. So we already know what TC is, 260, and TH is 300. So let's do some plugging and chugging. We'll say that, let's see here, W, I'm just going to take this equation right here, and we'll say minus QC is equal to W times 260, because that's the cold heat, or the cold temperature, over 300 minus 260. And if we work that out, it turns out that minus QC is equal to 6.5, because that's what that ratio turns out to be, times W. Well, now what? Wait a minute. So they're asking how much of that heat, let's see, it says it delivers 1,000 joules of heat to the room. Now this is the only sort of thing that you need to practice with, which is what we're practicing with right now, and that is delivering 1,000 joules of heat to a room. That is QH. Clearly, I mean, we're delivering the heat to the room. We're using a heat pump, so this is the part we're trying to heat up, so they're telling us directly that this QH is 1,000 joules. It's a shaky J there. Okay, so if we go back to this equation right here, we're told that QH is 1,000. Great, check, okay. But wait a minute, we don't know what minus QC or W are, because all we could figure out was this. But if all we could figure out is this, and guess what? Look, minus QC. What is minus QC? Well, it tells us right here. Minus QC is 6.5 W. So let's put that here. We'll say minus QC is 6.5 W. Okay? And then we have the rest of the equation, which is plus W. Right? So we've just, this part goes here, this part goes all the way here, and this part stays just the same. Well, look, what's 6.5 W plus one more W? It's 7.5 W. And that's equal to 1,000 joules. So now, okay, all we have to do is rearrange a little bit, and we can say that 1,000 joules divided by 7.5 is equal to W, and what is that equal to? 133 joules is W. Now, they say how much, so we're throwing out 1,000 joules. How much of that was work? Well, 133 joules was work. So we got 133 joules. So what is minus QC? Well, it's pretty clear. It's got to be, let's put that in green, this plus this has to be 1,000. Well, it turns out that minus QC then has to be 867 joules. Why? Because 867 joules plus 133 joules is equal to 1,000. So we can take a lot of energy out with just a little work and throw it away. And so this is a pretty efficient heat pump. Remember though, only when this cold temperature and hot temperature are pretty close together. And that's what we're seeing. These are only 40 degrees apart. So this is working quite efficiently. But if those temperatures were very different, you'd see that this would not be working as efficiently at all. Okay, so now let's work this last problem, which is a little easier. An ideally efficient steamboat engine operates at 500K steam in 300K weather. So really what they're saying is TH is 500K. And the cold reservoir, that's the other side, that's got to be at 300K. That's TC. So they're giving us the specifics here. How much work can this steam engine obtain when 1,000 joules of heat leaves the steam? Well, first let's draw that picture for an engine, because they're clearly telling us this has got to be an engine. We know this is minus QH, because remember that's coming out. Here we go. There's our QC, and there's our W. So they're saying 1,000 joules of heat leaves the steam. What does that got to be? Well, it sure isn't what we're throwing away into the cold reservoir. It's actually minus QH is equal to 1,000 joules. Now, remember, we have a different set of equations for engines as opposed to heat pumps. So we're going to write down the proper equations here. And this one says whatever we've got coming out of oops, look at this. I have a little error. That should be minus QH. So minus QH is coming out of here. We're going to take out the work so that it's minus W. And that's just the way we're defining things here. And whatever's left is our QC. So we've got that. And now we will say the second equation, which is just W is equal to minus QH, TH minus TC over TH. Okay, got that? There's our two equations. Check, check. So what this is actually saying is whatever that heat is that we're pulling out, some fraction of it determined by these temperatures is what we can convert into work. This fraction right here is dictated by the laws of thermodynamics, by that second law, right? Entropy. And what that really is saying is you'll never get complete and total transfer of all that energy into work because you simply can't ever get this fraction to be equal to 1. Okay, so we're going to say work. We're going to plug in directly to this equation right here. Our work is going to be, and remember they told us Q8 minus QH is 1,000. Here we go. Let's put in 1,000 right there, joules. And let's get our fraction. 500 minus 300, right? Because I'm plugging in the temperatures, divided by 500. And when you work this all out, that turns out to be a fraction that's 2/5. So we're going to take that, multiply it by our 1,000 joules, and guess what fraction of this energy we can pull out as work? 400 joules. So we took 1,000 joules out, but we could only convert 400 of it into work. The rest we had to throw away as waste heat in order to maintain the or just keep everything in accordance with the fact that any process must inevitably create more disorder overall. So we still, if we're making some order locally, we still have to throw away heat overall to create a further disorder as a consequence of this process. So That's just the background. If you just want the actual numbers, this is how to get them.